السلام عليكم ورحمة الله وبركاته. ما شاء الله ما شاء الله. 7 guys already in the classroom. Very good. Let's see how many will reply to my salam. Only one so far. Two, three, four, five. MashaAllah. I think there were 7. Now I can see only 5. I think the best among you is the one who said the complete reply. Wa alaikum salam wa rahmatullah wa barakatuh. Because فحيوا بأحسن منها أو ردوها. So give the same or better. So the same will be the complete. Okay. I'm not feeling well today. Maybe you can notice from my voice slightly different. I am using the mask, so I will try without the mask to see if it works. If I feel too cold weather, then I probably use the mask. Okay, I think I'm not the only one. I think we have several guys. I think this time the weather is changing. Cool, hot, rain and stuff. So, Jazakumullah khairan. Thank you very much. جميعا إن شاء الله. So, well, this is a reminder always from Allah subhanahu wa ta'ala for the person to come back to, get closer and make dua and stuff. Especially with for those who really get farther. Jazakumullah khairan. Thank you very much. Okay, even somebody was telling me, just cancel the class. Sorry for this. I cannot just cancel the class. When I cough sometimes, I have to anyway, so I disable the mic and so I can have my freedom to use the tissue. Okay, so today I think it's going to be a little long lecture, even though somebody was telling me, oh, just be I don't know. My idea is I need to cover whatever I feel satisfied with. And really, when I want to cover to feel satisfied that I have covered enough, takes time. And some students, I hope they are willing to learn and focus on what I say and explain, and then go ahead and read it even further, because especially this subject, this digital system, mathematics, operating system, the stuff that has calculations, which we will see the operating system next time. There are some calculations to be made, and there is some procedure for them. So that needs practice. You have to practice, especially in the digital. You have seen number system a new language. How much time did it take you to learn the decimal number system when you were a little kid? So now the kid learns better, well, to some extent. But of course, because the older person can, they can use logic, they can relate things, they have more knowledge to refer to, so it's probably easier also. But still, it's a new system. Okay, now 5 minutes already. Let's see. I think we had two more people that disappeared. They were 7. But anyway, do you know, guys, that even when you join and leave, the time will show. I mean, the WebEx will capture the attendance, capture who was present from what time to what time, and how much time this person spent in the classroom. So that all counts. So let's try to, I think, unless it's some technical issue. Okay, without further okay, let's just go ahead and share the digital systems book and continue from where we left, inshallah. Okay, I think we reached to the parity, was it? I think I said we are going to stop at 2.9, but then I said you have up to here, up to 2.10. I think we stopped at 2.9 because I did say the 2.10, chapter 2, section 10. Go ahead and read the contents there. But I think I would rather cover some parts. Okay, so let's go to chapter 2, section 10. A lot of notes on the sides. I hope you all have spent time with this. Guys, by the way, this really takes time. This takes time. So you have to spend time practicing, solving the homework assignment questions. After this lecture, we'll have lecture 4 and then the midterm exam. All right? So lecture 4, I think there are some questions from assignment 2. Okay? Because I don't want to have the exam only on the number systems. We want to have some logic gates involved as well in the midterm exam. So that is chapter 3, sorry, chapter 3, lecture 4, chapter 3. So please, you need to solve the assignment questions as soon as possible and spend time and take your time and try to understand what's happening. All right? I did mention that the answers are available. The answer book is available on the internet. The link that I have given you, libgen or genlib.rs or r or is, or so, just change the extension there. It's still working. It came back to work. I think last time it was not working anymore. Okay, let me just quickly check. Libgen dot or genlib, okay, genlib.rs. Last time it opened with me. So you can search there for the textbook, for the solution book. Check or search for the author's name. I think it's Libgen. Yes. The author's name is Tocci, Tocci. It's Libgen, I think. Libgen, because it's library genesis. Let me see. Yes, this one works. .is, whatever that is, and then .rs is the original one. Yes, it is also there. So if you put Tocci, Tocci digital. Oh, you're not seeing what I'm typing. Okay, you know, no problem, you understand. Just type in Tocci and digital. Then you will have 7 files. Among them, Instructor's Resource Manual for edition 10, which is the one we are using. Okay, so that is the solution manual. I would like you to get it by yourself. All right? Don't ask somebody else to do it for you. Guys, you are now, I think most of you are third-year students. So you are 3 years in the IT program, and you have been using the computer for how long? At least I would say 7, 8, 10, 15, 20 years, some of you. So those who have been using for a long time, no, I'm not worried about them. Those who are new and they still need to practice some more, please try. If you have any problem, then ask in the group. Somebody may help suggest something. So I can see even digital system edition 12, okay, is the latest edition 12, but we are using edition 10 because we have the solution book for it. It's the same book actually. They just modify just a little numbers here, they add some things, but this is going to be interesting if you go to edition 12. But edition 10 is the one that I shared with you, is highlighted. So make sure you use that one to help you when you study, inshallah. Okay, so lucky this libgen.rs is back online, because they always, they take it down, then comes back up, take it down, comes back up. So it's like, you know, it's always a fight between the people. Anyway, yeah, okay, let's go back to now. Okay, this is the ASCII code that was I left you on. Okay, 2.8. I think we finished 2.8 last time. Okay, got 2.9 parity method for error detection. Parity method. This parity method is used for, as the name says, error detection. Okay, what is error detection? When you transmit bits through the any transmission in zeros and ones, any transmission, there is bound to be some noise. The signal may be attenuated, some bits may be modified. So this is one way to check if there has been any odd number of changes. Okay, it's very awkward. Odd number of changes, or if one bit changed, we can discover it. We can discover that there has been a change of one bit. If there are two bits change, we cannot tell. If three bits change, we can tell, but we don't know what bit changed. So at least, the least the receiver can do is to ask for retransmission. Okay, so let's see how this parity method works. Okay, so when you transmit from transmitter to receiver, suppose you are sending this signal, then there will be some noises. Some noise, see this spike there and there. So this spike there, okay, this spike doesn't cause any problem because it's mostly like at the high side. So it's going up. Talk to us later, okay? After the class, inshallah. If this goes up, it is already high. But this one is the low signal part of the wave. It has, see this noise spike going up. This noise spike, we have seen from last time, the level for low is from 0 to 0.8. For high is from 2.4 or 2 to 5. So this definitely goes above 2. If we have a scale of 5, this goes to almost 2.5. So this point will go high. It will be detected as being high, which is supposed to be low. So then we can tell if the error happens. Okay, so let's see how this parity bit works. Okay, suppose, let's remove that. This is not centered. All right, so we have two types of parity. We have even parity and odd parity. Okay, odd parity. Basically, when we transmit characters as bytes, as one byte, okay, as 7 bits, as ASCII. We have seen the ASCII last time, the American Standard Code for Information Interchange. Every digit, every single symbol, every character will be transmitted as 7 bits ASCII, okay? Well, between the keyboard and the CPU, at least. Of course, when we transmit outside, then the different codes will be done. So for every 7 bits, we add an bit number 8 as the parity bit, depending on the content of the bits. All right? So here we have 1, 2, 3, 4, 5, 6, 7 bits. Then we add one parity bit. They become 8 bits. Now, let's see what we have here. So here we have 1, 0, 0, 0, 0, 1, 1. How many ones do we have in the original symbol or character? We have 1, 2, 3 ones. We have odd number of ones, but we want to use even parity. So to use even parity, we need to make the number of ones even. So to use even parity, we need to make the number of ones even. So here we have 3 ones. We need to add one more one to make them even. So when we add one, then becomes 4 ones, even number of ones. So when we transmit to the other side, the system, the receiver will check these 7 bits. They will find that, oh, these are odd number of ones. It expects to get a 1 value in the parity bit position. If it finds 1, then it means this is most probably okay. Most probably okay. It will take it. This is just one way. It's not a very efficient way, but it is good for short distances where noise is not expected to be too much. All right? This is used mostly for serial communication or asynchronous communication. All right? So with the 7 bits, we count the number of ones in these 7 bits of the character. So based on the number of ones, we add the parity bit to make the total number of ones even, provided that we are using even parity. So both sides agree to use even parity. If both sides agree to use odd parity, then we need to put 0 there to keep the number of ones odd, which is 3. Even means 2, 4, 6, 8, 10. Odd means 1, 3, 5, 7, 9, right? Okay, so this is the idea of parity. All right. So let's see here. We are transmitting hex 41, the character A. Okay, character A is hex 41. Is it capital A? Go back to the ASCII just for a quick glance. Capital A is 41 hex, right? So capital A is 41 hex. So 41 is 100, that is 4, and 0001, that is 1. So this is the 1, this is the 4. So how many ones do we have? We have 2 ones, 2 ones only. So we want to use odd parity in this case. To use odd parity, we have 2 ones only, then we need to add 1 value for the parity bit to make them odd, so that they are now 3. All right. If we were to use even parity, we would put 0, so that we maintain or keep the 2 ones there, only 2 of them, even number. All right. So this is how the parity works. Okay. It's very simple. Another example here. Suppose this is what was transmitted. Okay, this whole thing will be transmitted, of course, the 8th bit will be transmitted. Suppose on the receiver side, the receiver receives this. So the receiver, it will automatically take the first 7 bits and check how many ones are there. We're using even parity. So we have 1. Then it expects to find 0, so that the number of ones will remain odd, right? So it finds 1 there. It finds 1. So there are 2. This 1 means the number of ones here should be even. So there may have been 1 that was turned to 0. In this case, this is what happened. Or maybe there was all zeros, and this one was by noise and became 1. So it doesn't know, but it knows that this is wrong. There is something wrong here, because the parity doesn't tally with the parity bit that is received, doesn't tally with the calculation of the parity bit needed for the actual bits for the character to be transmitted. All right. So this tells it that there is an error. Okay. Now I'm putting here, this is bit 0, bit 7. So the number of bits will start with bit 0 from the least significant bit. So this is bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. Bit 7 is the most significant bit, MSB. Bit 0 is the least significant bit. All right. So suppose this is the code of the character that we have, which is 1000011. So this is 100, that is 4 hex, 00113. So that is 43. Remember, A was 41, B will be 42, C will be 43. So this is the code for C, capital C. Anyway, if we want to use odd parity with this code for the character, then we have 1, 2, 3 ones already. So the parity bit for odd parity will have to be 0. So the number will not change. It will still be 4, 3. If we were to use even parity to indicate, the content of this code character, so we need, for even parity, we need to make the number of ones 1. So we have to add 1 to make them 4 instead of being 3. We need to make them 4 because we are using even parity. All right, it's so simple. Okay, but the receiver, if the parity bit calculation of the code received or of the character code received doesn't tally with the parity bit, it knows that something has been, there has been something wrong. So it will ask for retransmission. Okay. Now, example here, for instance, information usually encoded in ASCII. Okay, let's say we want to send the message hello, HELLO, using ASCII. Okay, so this is hello, H is 48, E 45, L is 4C, O is 4F. Okay, now this is 4, 8 hex, which is 100, that is 4, 1000, that is 8. Remember, 1, 2, 4, 8. 1, 2, 4, 8. So this is 8. 1, 2, 4. This is 4. Here, 1, 2, 4, 8. 1 and 4, 5. So that's why this is 5. That is 4, 4. This one, 1, 2, 4, 8. 4 and 8, 12. That is C. Remember, guys, you should already memorize the the code for hex characters or hex numbers in binary. Okay, the hex, for instance, 48, you should immediately know 8 is 1000, 4 is 100, F is 1111. Very quick. You need to go back to that table and memorize it. All right. I wish we have, maybe I will need to incorporate this, like we have an how do you call it, face-to-face exam. So I have, I see you in the camera, and then I ask you questions, and you respond immediately, verbally, without having to go to ChatGPT. When ChatGPT came about to this world, it's making life easier and less smart, making people more, how do you call it? I think you can use the word, three-letter word, more, no, it's four actually, more DUMB, which is opposite of smart, because you don't have to think. You just ask ChatGPT, give you the answer, and then use the answer. So, so please, guys, you need to memorize these numbers. You need to memorize. Inshallah, hopefully in the future, I will manage to change the university's policy and allow exams to be, over camera one by one. That will give very high credibility to your knowledge and to your certificate and to your grades. Because when you go to the meeting, interview for employment, and they ask you, you can answer, say, oh, because my university uses this system with me, with us. They make sure that we know very well, we understand, and we learn. Then you give a very good reputation to your university. This is what we're after. But as of now, you say online university, still they are not sure until they see many instances, many examples of people who graduated from that university, and they are good. Then they know, okay, this university is good. So, of course, there are exceptions. Anyway, so H is 48, which is 100, 1000. We are using even parity. Even parity. So count the number of ones. Here we have 1, 1, 2. 2 ones. So the parity bit will be 0 to get even parity. Here we have 1, 2, 3. We need a fourth one to make it even. So parity bit will be 1. So here we have 1, 2, 3. Parity bit will have to be 1, 4. 1, 2, 3. Parity bit will have to be 1. Here we have 1, 1, 1, 1, 1. 5 ones for the character O. So we need another parity bit of 1 to make it 6 even. All right, so that when we transmit this whole thing, the 8 bits will be transmitted. All right, now applications. Okay, please read this. Okay, this is easy to just calculating. Okay, now let's look at this question. It's related to the parity. Okay, serial COM port. Okay, COM port, we have COM and COM, we have, or even the USB, they call them COM port. It is COM because the serial communication, or communication port number 1, 2, 3, 4. Now my mic is port number 5. The parallel, what was it called? LPT. LPT, I think it was to be called a long time ago. It's been some time. LPT. Okay, logical parallel transmission or something like that. Okay. Now let's see. Suppose this is the stream of characters that need to be sent serially through the COM port, starting with the colon, then 1, then 0. Okay, so each one of these, it's 7 bits ASCII, will have to be added by 1 parity bit. We want to use even parity. Okay, so let's see the colon, the code for colon. Oh, this question for you actually, but okay, let's just look at the answer. The code is 3A for colon. 3A. Okay, can you verify if you have the book? Okay, only one student who didn't attend. This is the first time the student attends. They should see, the student should get in touch with the lecturer early, not during the class time. You have the link, you have the number, you have my number. And some students even have been my students before. Or you can get my email address. You can easily use it and then send to me any question. Don't ask in the class. Okay, so that you are prepared before the class. Anyway, so 3A is the code for colon. 3 is 011. A is 1010. Here, 011. for 3. 1 0 1 0 is the A. How many ones do we have there? 1 2 3 4. We're using even parity, so the parity bit will have to be 0. So this is 3 bits, and these are 4 bits. So this is 3A in binary. So hex 3 is 1011, A is 1010. So we need for the parity, even parity bit will have to be 0, so the number will remain the same. Okay, for the next one, the next will be 1. 1, what is the code for 1? It's 31. Okay, I think it's 31. Do they show it here? Okay, let's see. I think I remember it to be 31. Go into, okay, number 1 here, 31. Okay, we said A was 41, C was 43. We noticed today even H was 48. Remember? So number 1 is, see the character 1 is 31, which is 0011 0001. Okay, so back to the example, or to the question actually. So they're asking, I think, about the first one. Okay, so we have for the 1 0. Okay, let me type. When I do this, I lose a lot of time. But okay, sometimes. Okay, let's come back here. So for the 31, oh, I have it there. Okay, I forgot that. I have done it long time ago. 31, which is 011. Okay, sorry. 011 is the 3, and 0001 is 1. Okay, how many bits, how many ones are there? 1 2 3. We have 3 ones, so we need a 4th one to make it even, to make the number of ones even, using even parity. So this is a parity bit, which is 1. So we have 1011 0001. What does this number become? 1011 is B. So this will become B1 will be transmitted. Actually, it will be like 1011 0001 that will be transmitted. But when we represent it in hexadecimal, B1 will be transmitted for the 3-1. Okay, there will be a question like this in the quiz, I think, and all the exam. All right, so make sure you know this. All right, okay, so the rest of the questions. Okay, let me see, comment, use the pencil pointer. B, okay, what is B? The value 10 total hexadecimal number per byte. Okay, what is the decimal number of bytes being loaded? Okay, the value 10 decimal, following the colon. Oh, okay, 10, which is following the colon. Where is that? 10, 10. So 1 is a character, 0 is a character, 0 is a character, 2 is a character, F is a character, 7 is a character. Each one of them will be transmitted using the 7-bit code, ASCII code, plus the parity bit, which will be bit number 8. All right? Okay, actually bit 0 to bit 7, which is the 8th bit. All right? So the value 0 following the colon 10 represents the total hexadecimal number of bytes. Oh, okay. That are to be loaded in the micro's memory. Okay, so usually after the colon, this will give you, okay, the number of bytes that are following to be loaded. So this is like a code. All right, so 10. So what is the decimal number of bytes being loaded? Decimal numbers. Sorry, I need to. What is the decimal number of, okay, this is 102 to represent the total hexadecimal number. Okay, now it makes sense. Okay, now it makes sense, because 10 is the total number of hexadecimal number of bytes. So this is hexadecimal 10. 10 in hexadecimal, how much is it? So this is 116, right? 256, so 16 to the power 0, 16 to the power 1, 16 to the power 2. So say we have 10 number in hex for the total number of bytes. Okay, so this should give us 16, is it? 16 decimal bytes, 16 actual bytes, but we say 10 in hexadecimal. Okay, you do the rest, you read the rest. All right, I think let you read the rest. I think there is one. Yes, this one I want to go over. Please read all these applications. All right, they are straightforward. Just need to read. You know English. I know some of you their English is no. It's not you guys. You are good. You are good because I was listening to one student from the reading the instructions as my style. The students' English is not that good. I don't trust them to be able to read and the textbook can understand and follow what they are reading. That's why I insist on you reading out loud so that you practice. Okay. Uh, what is this? Okay, let's just quickly look at this. Okay, so when we transmit serial transmission, okay, the serial transmission is usually we use asynchronous data communication for serial communication. Okay, the ASCII code will be transmitted like this. We have a start bit, we have a stop bit, we have parity bit, and the 7 bits. So we have the start bit, that is 0. Then we have 7 bits, that is data bit 0, 1, 2, 3, 4, 5, 6, 7 data bits from 0 to 6, followed by the parity bit based on the content of these data bits. Then followed by a stop bit, which is high. So this is fixed starting bit after being idle for some time, idle high for some time. Then when it goes low, it means we're starting the transmission. This will be followed by 7 bits and the parity bit. Parity bit depends on the content of these bits. Okay. Then we have a high stop bit, and then we have idle for some time. All right. The total number of bits will be 7, 8, 9, 10. 10 bits for every character. 10 bits for every character. Okay, so that is not bit per second, it is like the character per second. Character will be 10 bits in this case. So the start bit is always 0 in this example. The stop bit is always 1. Parity depends on the content of this. Let's look at this. So this content is 1, 1, 1, 3 ones. The parity bit is 1, which means make the ones 4 even. So this using even parity, right? It's pointed there, even parity. We have 3 ones. Then we need to add another 1 as a parity bit to make the number of ones even. All right, I think by now, guys, it should be clear. Read these, redo them as a study. Okay, now chapter 3 is finished. Chapter 2, not 3. Chapter 2 is finished. Summary of, okay. Now, do please all this, no, I think I gave you the assignment. Okay, let me see, undo that. Don't use calculator. Okay, don't use calculator only to verify. Okay, as I showed you last time, the time before last, when you guys, I didn't come back from the calculator to the PDF in the WebEx, but you know, and then nobody alerted me, and I got anyway. I told you last time. Show your detailed work. Always show the detailed work. If it is so simple, you don't have to make it too simple. But if there is some intermediate steps, you have to show them. All right, unless it is very straightforward. Okay, so show reasonable details to show that you know what you are doing, and to show me, to convince me that you know what you are doing. Okay. Okay, so I think this is just, I mean, if you want to practice more, you can do this. Okay, adding by the numbers, subtract by, okay, we will go to that now. So now chapter 2 is finished. Please read all of chapter 2, okay, including the parts that I left for you. I trusted you to read them, so I think you are good guys, and you are mature enough to be able to do what is asked of you. Okay, now let's go to chapter 6. Jump to chapter 6 and then go back to chapter 3 afterward. Okay, chapter 6, see, binary addition, because this talks about numbers. I don't know why they have this arrangement. I think maybe in later versions, this part of chapter 6 will be added to chapter 2. Or maybe they wanted to give the reader a break from the numbers, so they go to other things, and then they come back to the numbers, you know, but I think now is the best time to cover this. Binary addition is very simple. I gave an example earlier. Okay, binary addition, just like the decimal addition. 6 plus 1, 7. 7 plus 6, 13, right? We have 3 and 1 carry, which is that 10. So the 10 or 1 plus 3, 4 plus 4 is, so that's 8. You know how to add in decimal, right? I think some people forgot how to do that because they are using the calculator. This calculator is pain and a boon. I think it's good and bad. Good because it helps you, makes things easy, but then bad because it doesn't allow you to use your brain if you use it for everything. No, always make sure you experiment to exercise your brain. Okay, for binary addition, we have seen that 0 plus 0, 0. 1 plus 0 or 0 plus 1 is 1. 1 plus 1 is 2. How do I write 2 in binary? That is 1, 0. So this value is 0, sorry, 1, 2. Remember 1, 2, 4, 8. So this is 1 and this is 2. 0 ones, nothing. And 1, 2. So we have 2. So this is 2, which is 0 plus 1 carry to the next position, just like we have done there. So for the 1 plus 1 plus 1, 3. 3 is 1 plus 2 carried to the next position, which is another 1, which is 1. So it becomes 3. So this is how we say 3. So 1 plus 1, 2, plus 1, 3. So we have 1 with 1 carry. 1 will have nothing to add to, so it just comes down. So 1, 1. So 1 plus carry of 1 to the next position. All right, we'll see when we have, okay. Now we have multiple bit addition. Guys, all of this you have to do by hand on paper. I have been dealing with digital systems for more than, okay, let me see, since 1980, 1981, 1980 or 1979, I think. I've been dealing with this and extensively the last so many years when I was teaching the digital systems. So I know them by heart. Sometimes when I get so tired, I'll make a mistake. Everybody makes mistakes when they get tired, don't you? Okay, so, but it takes a lot of practice. So you have to do this by hand on paper. All right. Now, 0, 1, 1 is 3. This is binary, this is decimal. 1, 1, 0 is 6 because we have 1, 2, 4. 2 and 4 is 6. All right. You need to know this by heart. Let's add them. 1 plus 0, 1. 1 plus 1, 0 with 1 carry. 1 plus 0 plus 1, 2. That is 0 with 1 carry to the next position. That one comes down. So it's 1, 0, 0, 1. That is 1, 2, 4, 8. 1, 2, 4, 8. 8 plus 1, 9. That is 9. So this is what we're supposed to get. This one, we have 1, 0, 0, and that is 1 and 8, 9. 1, 1, 1, 1 is 15 or F. 1, 1, 1, 1 is 15. That's 1, 2, 4, 8. 15. Let's add 9 plus 15 will be 24. Should be. Let's see. 1 plus 1, 2. That's 0 with 1 carry. 1 plus 1, 2. That's 0 plus 1 carry. 1 plus 1, 2. That's 0 plus 1 carry. 1 plus 1 plus 1, 3. That's 1 plus 1 carry. Carry comes down. So there's nothing to add to. So it's 1, 1, 0, 0, 0. So this is 1, 2, 4, 8, 16. 8 plus 16, 24. This is 24. All right. So you will have addition questions in the assignment, quiz, and the exam, and all the exam. Okay. Now he also adding the decimal. I mean the numbers after the binary point. Even though we used to call decimal, now this is binary point. All right. With decimal is decimal point. Here it's binary point. Addition is exactly the same as we do in decimal numbers. So 1 plus 0, 1. 1 plus 1, 2. That is 0 with 1 carry. 1 plus 1, 2. That is 0 with 1 carry. 1 plus 1, 2 plus 0. That's 2, which is 0 plus 1 carry. 1 plus 1 plus 1, 3. That is 1 plus 1 carry. 1 comes down. So this is the number. This is 0. Sorry, 1, 2, 4. So this is 6. This is 1, 2, 4. Then this is half, quarter, 1 over 8. 1 over 8 is 0.125. All right. Okay. So this is binary addition, very simple. Always make sure you do those review questions. Okay, now we'll be dealing or looking at signed numbers. Numbers, so far we have been dealing with numbers that are unsigned. Numbers that have been unsigned. Okay, let me see. How many are still with me or are already 1, 2, 3, 4, 5, 6, 7, 8, 9? MashaAllah. Okay, 9 people. Guys, are you still with me? Let me see some replies. Yes, okay, okay, MashaAllah. The others? Yes. Guys, you have to really pay attention. And also, I think you will also need to review or to watch the recording a second time. Also, sometimes you may need to go to WhatsApp and check on binary addition, for example. Anything that you want to ask about, go to the YouTube. I said WhatsApp? To the YouTube. See, you go to the YouTube and ask for binary numbers for beginners or whatever it is that you want to ask about. All right. So go to the YouTube, and there are wealth of even digital systems course consisting of maybe 50, 80, 100 lectures you can find there. Everything is there on the YouTube. Many different people doing that because it is easy to do. I can do that, but then it is so much done there. So anyway, so whatever you want to ask about, whatever you want to have more information about, whenever you want to get more point of view, if you like, go to the YouTube. But make sure you go over this first. Okay. Now, signed numbers, we have so far been dealing with unsigned numbers. We don't worry about the sign, so everything is positive. Unsigned means all are positive. Now, let's look at signed numbers. One type of signed numbers is called sign magnitude form. Okay, only this, just a little bit about this. Where you have the magnitude, okay, this is the magnitude, and this is the sign. Sign bit is always the most significant bit. The sign bit, always the most significant bit, the leftmost bit of the character or of the code. All right. So this is the amount or the magnitude. This is the sign. Sign positive is 0, negative is 1. Positive sign positive indicated by 0, negative sign indicated by 1 in the sign bit. All right. The other bits, okay, this is magnitude. This is 0, 0, 1, 0, 1, 1. We have 1, 2, 4, 8, 16, 32. 32 plus 16, 48 plus 4, 1, 2, 4. 48 plus 4, 52. So this is 52 positive. This is the same one, 0, 0, 1, 0, 1, 1, or 1, 1, 0, 1, 0, 0. This is the same magnitude, 52 negative. Okay. So which number of systems you use to indicate the positive and negative depends on, your application or your implementation. So this system is called sign magnitude form, where you have the magnitude always the same. Only the sign bit will tell, is this a positive number or is it a negative number? 0 means positive, 1 means negative. All right. That's it for this sign magnitude form. Okay, we're more interested in 2's complement form. Computers use 2's complement number system. Binary numbers using 2's complement signed number system. What is 2's complement? This brings us to what is 1's complement. What is 1's complement? 1's complement is basically just the opposite of the original number. Original binary number is this one. Let's say 101101. The 1's complement, we just invert, we convert, we complement, we negate. Okay, complement is the word to use because that's 1's complement. Okay, complement of each one of them. The 1 becomes 0, the 0 becomes 1. So this will be the 1's complement. We just change the 1 to 0, the 0 to 1, 1 to 0, 1 to 0, 0 to 1, 1 to 0. So this is now called 1's complement form of this value, whatever it is. What is that value? That value is 1, 2, 4, 8, 16, 32. 8 plus 32, 40, plus 4 plus 1, 45. So this is 45. This is 1's complement of that value. Just complement each bit. 2's complement, we add something else, we take the original number, then 1's complement, we add 1 to it, plus 1. This will make it 2's complement. So this is original number, so value 45. This is the 1's complement. We add 1 to the 1's complement. So 0 plus 1, 1. Then this will be added with nothing or zeros. So it just comes down. So the 2's complement of this number is this. Normally we use 8 bits. I added this. So to make it 8 bits, for instance, here we have 6 bits. Right? 2, 4, 6 bits. To make it 8 bits, we add 2 zeros to make it 8 bits. Why this can be sometimes an issue? Because if the number is supposed to be negative and it doesn't have 1 on the leftmost side, okay, normally the negative number has 1 on the left, as we will see. The positive number has 0 on the left. So if we want to extend the number to 16-bit, we just repeat the sign bit. The same magnitude will not change. The same value of the number will not change. If we have minus 10, 8 bits minus 10, we want to make it 16-bit. We just repeat the sign bit, which is 1. Becomes all 1, 1, 1, 1, 1, 1, 1, 1. The value will not change. All right? So you follow what is written there, because sometimes I may jump back and forth, but your reference is the text that is there. So this is original number, 1's complement, plus 1 becomes 2's complement. This is 2's complement. Okay, your clue will be the examples and how they are solved. Now, original binary number, this is a different number. See, that is 1101, this 1100. So this is a different number. This is original binary number. 1's complement, just change the 0 to 1, 0 to 1, 1 to 0, 1 to 0, 0 to 1, 1 to 0. These big ones are from me. Then add 1. So this is 1's complement. We change the 0 to 1, 1 to 0. Then we add another 1 to get the 2's complement. So 1 plus 1, 0 with 1 carry, 1 plus 1, 0 with 1 carry, 1 plus 0, 1, and then 0, 1, 0. So this is the 2's complement without that one. This big one there is from me. So this is the 2's complement number, 2's complement representation of the original number. So the original number, we make 1's complement, add 1 to get 2's complement. This is the strategy to go. Original number, take its 1's complement, add 1 to the 1's complement, we get the 2's complement number result. All right. I'll come back to this maybe a little later when we have more talk about that. We'll talk more about that. Okay. Now, let's see. We want to convert. Okay. This is okay. Represents odd numbers, use the 2's complement. Okay. We have value figure 62. Okay. This is plus 45. This is minus 45. Plus 45 is positive. So 45 is the combination from this 1, 2, 4, 8, 16, 32. That will give us 45. 45 will be 32. We cannot have 16 because it will be 48. 32 plus 8, that's 40. Plus 4 plus 1. We get, so 1 is 1, 4 is 1, 8 is 1, 32 is 1. The others are zeros. And this is 0 there. Okay, so this is 1, 2, 3, 4, 5, 6, 7 bits. The 8th bit, to make it 8 bits, will still be 0 because this is positive. To get the negative, okay, I think, do they show? Sometimes I forget the exact details that they have there. Okay, from positive to go to negative 45. What do when we say negative 45? We do the 2's complement. Okay, if the number is okay, if the number is positive, the magnitude is represented in its true binary form, and sign bit of 0 is placed in front of the most significant bit. This is shown in here. Okay, so this is the sign bit. Still, these are 1, 2, 3, 4, 5, 6, 7 bits. Okay, with bit 8 will be just repeating the most significant bit. Now, minus 45. How to get minus 45? How to get minus 45? This is This was what? This was 45, right? See, 32, 8, this is 45. How to get minus 45? This is minus 45. Because we take 1's complement, add 1 to get the 2's complement. This is now minus 45. Without looking at that, this is minus 45. But because we will have to have 0 there, add 0, complement it to 1. Then when we add 1, all this will come down. So this one will come down. So it will be 1, 0, 1, 0, 0, 1, 1. And then we can add another one. We can extend the sign without having the number changed. Extending the sign bit does not change the value of the number. All right. So this is the minus 45, which is what we had there. So this is, let's see, from right, 1, 1, 0, 0, 1, 0, 1. 1, 1, 0, 0, 1, 0, and that's my one for the sign bit. Okay, to show the sign bit. So in the sign bit, for the negative number, putting 1 doesn't change its value. For the positive number, putting 0 as a sign bit doesn't change its value. For the positive, 0 doesn't count. For the negative, the one leftmost, we will see that it doesn't count because it is only a sign bit. It doesn't have a value. Okay, let's just look at this. Now, this is 45. One quick way to know the value quickly. This is 45. How do we know this is 45? We just use 1, 2, 4, 8, and then we take the value of ones. So this is 32 plus 8, 40, plus 4, 44, plus 1, 45. It is a positive, so this is 45. For the negative, there is a trick. The negative, we found that the negative 45 is this, using 1's complement plus 1, we get the 2's complement, which is minus 45 in 2's complement form. This is 2's complement form of minus 45, which is this same one. Okay, when you study, you need to inspect, to go back and forth and compare back and forth to see how this is happening. So now we know that this is now minus 45. This is minus 45. How do we know the value of this minus 45? Of course, they say, you know, where is your right ear? Or go around and say, oh, this is my right ear. You can say, this is my right ear, straight away. So they go, again, you want to see this, you given a negative number, 1, 0, 1, 0, 0, 1, 1, and you're not told what it is. And they say, this is negative number. What is its value? They say, okay, take 1's complement, add 1, bring it back to the original. Because we do the same thing to go back to the original. From negative, take 1's complement, add 1, get the original from that. You get the original. So instead of doing that, we just look at the zeros, the value of the zeros. The value of the zeros. This is again 1, 2, 4, 8 as usual. Then this is 4 plus 8 plus 32. 32 plus 8, 40 plus 4, 44. We need to add 1. So it becomes 45. So this whole thing is minus 45. So to know the value of any negative number, that is 2's complement signed number, which is negative number, to know its value, look at the value of the zeros, add them up, and add 1 to them. You get the negative value. This is to verify your answer. Okay, please practice doing this. All right, so we will see in the coming examples, inshallah, try to implement this as well. Okay, now this example says, okay, represent each of the following signed decimal numbers as signed binary numbers in the 2's complement system. Okay, use total of 5 bits. All right, so plus 13. What is plus 13 in using 2's complement number system? The positive is the same. The negative is different. So plus 13 is just normal 13, which is 1, 2, 4, 8, 16. We have, how do we get 13? We get, this is maximum 15. So we have 8 plus 4, 12, plus 1, 13. So we have 1, the 2 is 0, 4 is 1, 8 is 1, 16 is 0. So this is 0, 1, 1, 0, 1, 13. Okay, which is 1, 2, 4, 8, 1, 4, 8, 1, 4, 8, 8 plus 4, 12 plus 1, 13. So this is plus 13 in binary. The sign is this positive. The leftmost is the sign bit. all right, for the 13. For the minus 9, we start with 9, we take 1's complement, then we add 1. So we start with 9, 9 is 1001. Again, 1, 2, 4, 8, 1 plus 8, 9. Take the 1's complement, so 1 becomes 0, 0 becomes 1, 0 becomes 1, 1 becomes 0. Then add 1 to that. So now this is 1's complement, add 1 to it, 1 plus 0, 1, the rest comes down, so it is 0, 1, 1, 1. This is 0, 1, 1, 1, but we need to add 1 to indicate, because we need 5 bits. Okay, it's asking for 5 bits. We need to add 1 to make it look negative also. So this is 1, 0, 1, 1, 1. This is the, what is the value of this? Minus 9. How do you know? Okay, say 1, 2, 4, 8. This is 8. The number of 0, the value of 0 is 8. We add 1 to it, 9. So this is minus 9. This is the quick way to know the value of the negative number. Okay, so we attach the sign bit of 1 to make it 5 bits. So minus 9 is this one, 1, 0, 1, 1, 1. 1, 0, 1, 1, 1. All right? Now you need to do this, maybe more than once, for this thing to stick, because now you're not used to dealing with negative, you're not used to dealing with binary numbers, and then negative also to add to it, so it becomes a bit more difficult. So you need to practice. This is very important. The computer works using 2's complement number system. 2's complement number system. That's how the computer works internally. Okay, so this is minus 9. Now C, what is question number C? Oh, this is 3. 3 minus 2 minus 8. Okay, 3 minus 2 minus 8. 3 is 0, 0, 0, 1, 1. We know this 5-bit positive plus 3, nothing to do there. It's straightforward. The minus 2, we start with 2, which is 0, 0, 0, 1, 0. That is the 2. So 0, 0, 0, 1, 0. Because this is 1, 2, 4, 8, 16. The 2 is only there because we have value of 2. This is 2. Take 1's complement. Complement every bit. Then add 1. 1 plus 1, 0. Add 1 carry. 1 plus 0, 1. Then the others come down. So it's 1, 1, 1, 1, 0. This is minus 2. So that is 2. Take 1's complement. Add 1 to get the 2's complement representation of minus 2. So this is minus 2. If you are just given this value, like you have there, 1, 1, 1, 1, 0, 1, and you are told this is a 2's complement number, what is the value of this 2's complement number? So we just come, okay, this is 1, 2, we just want 2. Because we know this is negative because of that. So we are interested in the zeros. So this 0 value is 2. So we add 1 to it. So this is going to be minus 3. Minus, I'm ahead of myself. Okay. Where is minus 3? Minus 3 is, where was it? Did we see minus 3? No. Why am I talking about minus 3? Anyway, so this is now minus 3. Because this is 1, 2, 4, 8, 16. We don't need the others. This leftmost bit is 1, which means it is negative because we are told this is 2's complement signed number system. 2's complement is a signed number system. It has to, the leftmost is the sign bit. So if it is positive, that will have to be 0. If it is negative, that has to be 1. So if it is negative, and that is 1, then we just take the value of the 0, add 1 to it. So this value of the 0 is 2, so this number is minus 3. Okay, this number, okay, let's remove, okay, let's undo. Okay, suppose this is the number that we want. So this number is negative because it's 2's, we are told this is 2's complement number, and it is signed. The 2's complement number is signed, so it is signed 2's complement number. Whenever we say 2's complement, then it is the signed number. Okay, so this one means it is negative. Now this is 1, 1, 2, 4, 8, 16, right? So this value is 1, so add 1 to it, so this is 2. So this number is minus 2, which is that 1, 1, 1, 1, 0. 1, 1, 1, 1, 0. This is a shortcut. It's not mentioned there. But I mean, by inspection, if you inspect this you look at the value of the zeros, they are 1 less than the actual value of the negative number. So we have to add 1 to get the actual value of the negative number. All right? Okay. Now, minus 8, is it? Minus 8. We want minus 8. Minus 8 will be, okay, let's see what it will be. What is 8? 1, 0, 0, 0. That's 1, 2, 4, 8. So we have 1, 0, 0, 0, and there's 0 there because 5 bits. So 0, 1, 0, 0, 0. This is 8. 1's complement, reverse 1 to 0, 0 to 1. Then add 1. 1 plus 1, 0, 1 carry, 1 plus 1, 0, 1 carry, 1 plus 1, 0, 1 carry, 1 plus 0, 1. Then that 1 comes down. So it is 1, 1, 0, 0, 0. This is the minus 8. This is the minus 8. Suppose you were given this 1, 1, 1, 1, 0, 0, 0. What is this value? This is 2's complement signed number. What is its value? We know this is negative because of that one. So we just look at these values 1, 2, 4. 1 plus 2 plus 4 are 7. Add 1 to them, 8. So this is minus 8, which is minus 8 there. If you add more ones, doesn't count because we only look at the value of the zeros and add 1 to them. If you're given this number and you're asked what is the value of this, immediately you see, oh, 1, 2, 4, 7, this negative, so this minus 8. If you want to do this the long way, okay, then you take 1's complement first. So this will be 1, 1, 1, 0, 0, 0, 0, 0, 0. Then add 1 to them, so this is 0. Add 1 to that. 1 plus 1, 0. 1 carry plus 1, 0. 1 carry plus 1, 0. 1 carry plus 0, 1. Then those zeros will come down. So this 1, 0, 0, 0, which is 1, 2, 4, 8. So this is 8. So you can go through take the 1's complement, add 1 both ways, from positive to negative and from negative to positive. You take 1's complement, add 1, you get the result. Or you just consider the value of the zeros and explain that. Say the values of the zeros is this much, so we add 1 to it, we get the full value of the negative number. I will feel very happy to see that written in the exam. Some students do that. Some really good students who pay attention and who want to learn, they do this. It's very simple. Some others who are not so good, they just ask their very best buddy, very best friend in this life, in this the ChatGPT. So please don't do that. Okay? Learn. I know many of you will want to learn and probably already know. I know some of you already have been, in this field for some time. But those who have this new to them, you need to spend that time learning. Okay, so I think I need to remove this. Probably it doesn't look nice. Also, even when I come back to look at this, what is this? That's why I just undo. If you want to see this again, take a screenshot so you can keep it. Otherwise, go back to the recording. But I think it doesn't look nice. Okay, let's remove the latest parts. Okay, maybe this is more understandable. Okay, sign extension, as I mentioned already, for the positive number, it has 0 as the leftmost bit. Add more zeros to the left, extend it to the left, doesn't change the value. For the negative number, it has 1 as the leftmost bit. Adding ones to extend the sign does not change the value because only the zeros plus 1 is the actual value of it. Because when you want to find its value, you convert them to 1's complement and then add 1. The ones will become zeros, so they lose their significance. So sign extension does not change the value. So if it is positive, add zeros, doesn't change the value. If it is negative, add zeros, doesn't change the value. Okay, because if you convert this, so this is 1, 2, 4, 8. So this is minus 9. 1, 2, 4, 8, negative. This is minus 9, which is 1, 0, 1, 1, 1. Do we have it there? 1, 0, 1, 1, 1. 1, 0, 1, 1, 1. C minus 9. We have done it already. Okay, this stuff is very nice once you grasp it, once you have enough experimenting practice, then you will feel very confident, inshallah. Okay. So negation, to negate, to find the negative value, you start with the value, you get 2's complement. Oh, okay. Do something else. Now, when we say negation, is converting positive number to its negative equivalent, or convert the negative number to its positive equivalent. We see this in the assembly language. When we say negate, NEG, meaning you get the 2's complement number system. If we use complement, COM, means 1's complement. Both are used, actually. Both are used. They have their uses. So when we say negation, means convert from positive to negative, or negative to positive. This is negation, meaning negate the number from +9 to -9, or from -9 to +9. Okay, meaning we negate the signed binary number by 2's complementing it. All right. Okay. Example. Okay, I think I'll leave this for you guys to do. Can I leave it for you? Special case. Let's see how the range of signed. Okay, then 6.3 addition. Okay, addition is nice, easy. Okay, I think let's continue a little bit. Okay, each of the following numbers is a 5-bit signed binary number in the 2's complement system. So these are signed numbers, 2's complement system. Determine the decimal value of each case. Oh, decimal value, very quickly. This is positive. 1, 2, 4, 8. This is 12. Right? 12. This one, negative. This is 1, 2, 4. 1 and 4, 5. This -6. This is -6. See, what they do is they go from the negative, take 1's complement, 1 to 0, 0 to 1, add 1, you get that. Then find this value, which is 1, 2, 4. 2 and 4, 6. So this +6, then this must be -6. Why I have to go through that? Just get the value of the zeros. This one is negative. So this is 1, 2, 4, 8, 16. So 2, 4, 8. We know negative because of this sign bit, 5 bits. So this is the sign. So we take the number value of the zeros. 1, 2, 4, 8, 2, 4, 8, 2, 4, 8, 8, 2, 4, 10, 14. This is 14. So it's -15. We add 1 to it. -15. So this is -15. Very quick. I wanted to skip, but then I said, okay, let's look into it. I really didn't look through this before the class. Okay. So please, these things, read them. I think sometimes if you, some people, okay, different people have different ways of learning. For instance, myself, I used to learn from the lecture. In the class, when the teacher used to explain mathematics, for instance, or anything, alhamdulillah, I used to have, mashallah, my memory was okay. I used to remember. Some people cannot remember easily, so they have to write. Okay? Now I have to write. My memory is not as good as when I was young. Okay? So some people, I had one student in my class a few years back, many years back actually. He was a Chinese guy, and Chinese Malaysian. So his guy is just doing this. I say, why are you not writing out? That was an assembly programming class, microcontrollers. Why are you not writing the program? I write on the board. He said, well, I understand what you are doing. Are you sure? Yes. Okay. In the exam, he gets full mark. His CGPA was 3.99. 3.99. That guy, he has photographic memory. He understands and he remembers. But most people are not like that. I'm not like that. I don't remember. I still have to do the exercise, but some people are very exceptional, like, Imam Shafi'i, photographic memory. But most of us, ordinary people, we need to write. We need to write down. We need to practice. We need to solve. The more you solve, the more you learn, the more you understand, the more you talk about it, the more you discuss it, the more you learn, the more you internalize the knowledge. So you have to practice, please. And I think for the student who joined us for the first time today, I know you have the shock of your life here. It's just like coming into Japanese in the middle of the semester. So because when you don't start from the beginning, of course, things will be little not easy, little difficult. Okay, special case of two's complement representation. Okay, so this is 1, 2, 4, 8. This is 8 positive, right? If this is a positive number, this is 8. If it is a negative number, then this is 1, 2, 4, 7. So this is minus 8 as well if it's negative. So minus 8 is the same representation as 8. Minus 16 is same as 16. Of course, if you are limiting the number of bits without having additional bits. 32, this is 1, 2, 4, 8, 16, 32. So this is 32 positive. Negative, if this is negative number, then this is 1, 2, 4, 8, 16, 32. So this is 31 plus 1, 32. So it's the same representation. So 8 and its multiples, even the 4, 1, 0, 0. Why do I have to write with this handwriting? I mean, using the mouse. Mouse is so difficult. So let's say 4, 1, 0, 0, which is 4. Okay, if it is positive, so this 1, 2, 4. So this is 4 positive. If this is a negative number of 3 bits, so this is 1, 2, 1 plus 2, 3 plus 1, 4. So this 4 is equal to minus 4. Also, if you look at 2, for instance, 2, that is 1, 0. Is this equal to 2? This is 2 positive. That is 1, 2. So this is 2 positive. If this is a negative number of 2 bits only, so this value is 1 plus 1, 2. So this is also equal to minus 2. The same representation following this sign. All right. So even if we add more ones for the negative number, the value doesn't change. But of course, if it is positive number, the value will be a lot bigger, a lot different. So this is for 2 bits. Yes, please, if you have class, guys, you should have left on time. If you have class, you go to your class and you come back to watch the recording, please. After it is ready, which is 1 day after. So the recording will be ready tomorrow, 4 o'clock, inshallah. Thank you very much, guys. So please stay with me, those who don't have class. So we need to add to this for 2-bit number. Okay, let me make it smaller. Okay, 2-bit. Yeah. Oh, no space there. So for 2-bit number, here for 3-bit number, okay, up a little. This is for 4-bit number, 5-bit number, 6-bit number. All right. Then this is true. Negative is equal to positive. But for 8-bit, then we need to add zeros for the positive. We need to add ones for the negative. All right. So do these examples and you should be good, inshallah. Okay. Now, the complete range of values. Okay. If we have 8 bits, positive number, that's 2 to the power 8. That's 1, 256, 256, 2 to the power 8, which is 0 to 255. Okay. 2 to the power 8. 2 to the power 8 is equal to 56. Or 0 to 255. Because altogether 256 numbers from 0, because 0 counts until 255. If it is negative, it goes from -2 to the n. N is the number of bits. This is n. N is 8 there. N is 8. N equals 8. Number of bits. Okay. So minus 2 to the n, 2 to the n minus 1. So for signed numbers, for 8-bit signed number, let's see, sometimes okay, let me see. Okay, complete range of values that can be represented in the 2's complement number system having n magnitude bits. Okay, see, that's why, because something is not right. N magnitude other than the sign bit. Okay, that's why. So you have to read. Sometimes, this is tricky if you don't read to see what they're talking about. So this is the sign bit. Okay, let's see. Here we have 3 bits magnitude. Okay, 3 bits magnitude, and this is the sign bit. For 3 bits magnitude, 3 magnitude bits plus 1 sign bit, what are the values? Positive will go from 0, 1, 2, 3, 4, 5, 6, 7. That is 0 to 7. Okay, 0 to 7 there. This is positive. And for negative now, how much is this? This is minus 1. This is minus 1. How much is this? Minus 8. This is minus 8, minus 1. So f is 15 also, that's minus 1, because if this is a negative number, what is the value of 0 there? 0. 0 plus 1, 1. So this is minus 1. This one, okay, let's use the pencil pointer. So, pencil pointer. This one, this value of the 0 is 1. 1. So this is 1, 2, 4. So this is 1. Plus 1, 2. So this is minus 2. Here, 1, 2, 4. 2 and 4, 6. So this is minus 7. Which is that. All right. So for signed numbers, let's say we have 8 bits signed number, including the sign bit. That will actually be 1 sign bit plus 7 magnitude bits. So that's 2 to the 7. So for 8 bits, 2 to the power 7. Okay, 2 to the I need to hone, writing with the mouse. 2 to the power. See, this hat is power. 2 to the power 7 is 128. So this is 2 to the n, 2 to the 7. So that is minus 128. 2 plus 2 to the n minus 1. 2 to the 128 minus 1, 127. So minus. Okay, so this is, it goes from minus 128 when we have 8 bits, 1 sign bit, and 7 magnitude bits. So it goes from minus 128 to, okay, let's how to make 2. Oh, sorry, that is to 127. Minus 28 back to the 0 to the plus to 127. So altogether they are 256. If you find, you mean altogether, how many numbers are there? 256 from minus 128 to 127. Okay, which is from minus 2 to the power, n is the magnitude numbers. We remove the sign bit, then plus 2 to the n, 7 in this case, minus 1, that's 128 minus 1, 127. So we will have positive 0 to 127 and negative minus 128 until minus 1. All right? So this also shows that. Here the zeros value plus 1. Value of the zeros plus 1 will give the numbers decimal value, just like we have been doing. So this is 0, 0, 0, 1, 2, 4, 7 altogether, plus 1, 8. So it's minus 8 because it has 1 there, the sign bit. Okay. Range of unsigned, we have talked about that for 3 bits. For 4 bits, 3 bits, 0 to 7, 4, which is 8 altogether. 4 bits, 0 to 15, that's 16 bits altogether. For 8 bits, here the unsigned can be represented in a byte. Okay, talking about a byte. What is a byte? 1 byte is 8 bits. 8 bits, that's 2 to the power 8 to 56, which is from 0 to 255. 256 different values. All right? For the signed, again, we take the sign bit, okay, for the byte. So sign bit plus 7 value bits. So that is what we have done earlier there. Okay, you need to sit down and analyze. Get blank sheets of paper and pencil with eraser. I always see this eraser is always with me because whenever I want to do things, I use the eraser. I don't just scratch and fill it with scratches. No, I erase whatever is not right or I don't want. Okay, so this, I think we have talked about this already. Certain computer is storing the following 2 signed numbers in its memory using 2's complement system. See, 2's complement signed number system. So these are the 2 numbers, which is positive and negative. What is the value of that? That's 31. This one, okay. Let's use the pointer, the pencil pointer. While executing a program, the computer is instructed to convert each number to its opposite sign. Okay? So you need to change. How to do the change, the negation? Again, you go through 1's complement at plus 1, 1's complement plus 1. Okay, to do its negation. Okay, I think this, I think I'll leave it for you to do. We already know enough. Okay, examples here. What is, this is a negative number. What is the value? So this is 1, 2, 4. So this is minus 5. So this number, negative number, this is 1, 2, 4, 8. 1, 4, 8, 13. So this is minus 14. Okay, same thing for other numbers. Okay, plus 31, which is there. We want to find the negative 31 representation. Take 1's complement plus 1. So take 1's complement. This is 31. 1's complement plus 1. So it becomes 1, 0, 0, 0, 0, 0, 1, 1, 1. So this is minus 31. Okay. So now, please do all of these. Okay. Review questions you need to do really. Addition of 2's complement number system. Addition is straightforward. Okay, ask them to read out loud for all. Okay, do them while reading them out loud. I hope you didn't hear my cough. Okay, so to add, this is plus sign. Okay, to add, this is what you get. When you add the sign bit as well. Know that the sign bit of each number is operated on in the same manner as the magnitude bits. All right, so you just add the sign bit normally. So this is positive plus positive. So 1 plus 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0. So this is the result. So this is what? 1, 2, 4, 8. 1, 4, 8, 13, which is 9 plus 4. 9, 1, 2, 4, 8, 9. 0, 0, 1, 1, 2, 4. This is 4. So 9 plus 4, 13. So this is 13. So this is the result. This is the sign bit. So positive plus positive, we get positive. All right. Now, this is 2 positive numbers. Suppose we add positive number and smaller negative number. What will the result become? So this is 9, positive 0, 1, 0, 0, 1. Minus 4. How do you represent minus 4? Minus 4 will be 0, 0 there, meaning 3, 1, 2, 3, and then 1, 1, 1. So this is negative, and this is minus 4. So 9 plus minus 4 will give us 5. Okay, let's add them. 1 plus 1, 0. Oh, sorry, 1 plus 1, of course 1 plus 1 is no, this 1 plus 0. 1 plus 0, 1, 0 plus 0, 0, 0 plus 1, 1, 1 plus 1, 0 with 1 carry, 1 plus 1, 0 with 1 carry. We discard that because we're using only 5 bits. So this is 9 plus minus 4. The result is 1, 2, 4, 5, which is correct. The positive number plus smaller negative. If it's larger negative, then it's not the same. All right? Okay. So let's see. Positive number and larger negative number. So let's say we have plus 4 added to minus 9. So minus 9 is this 1, 2, 4, 8, 16. So this 8 add 1 to it, so becomes 9. So this is minus 9. This is 4. 1, 2, 4. The 1 is 4. So for the negative, we look at the value of the zeros. We add 1 to them. For the positive number, we look at the value of the ones. All right? So this is 4 plus minus 9. What is the result? 1 plus 0, 1. 1 plus 0, 1. 1 plus 1, 0 with 1 carry. 1 plus 0 plus 0, 1. 1 plus 0, 1. So this is the result. What is this result? This is 1, 2, 4, 8, 16. So this is negative number because this is 1. So 1, 2, 4. 4 plus 1, 5. So this is minus 5. So minus 9 plus 4, we get minus 5. So the result is correct. All right. Now, two negative numbers, negative plus negative, we should get negative, right? So minus 9, this is minus 9. This is minus 4. Add them up. 1 plus 0, 1. 1 plus 0, 1. 1 plus 1, 0 with 1 carry. 1 plus 1, 0 with 1 carry. 1 plus 1 plus 1, 3. 1 with 1 carry. The carry out of the 5 bits that we are using goes out. So this is the result. So still negative number. Negative plus negative. How much is this value? That's 1, 2, 4, 8, 16. 4 and 8, 12. Plus 1, 13. So this is minus 13, which is minus 9 plus minus 4, which is minus 13. All right. So this is addition that you just need to do straightforward. And the numbers will be specified. The number of bits will be specified. So if you're asked, okay, using 6 bits, then bit 7 you just throw away. Okay. Then equal and opposite numbers. Equal and opposite numbers. What do we get? As you may expect, you should get 0. So this is minus 9. This is plus 9. This is positive. So 1, 2, 4, 8, 1 and 8, 9. So this is negative. We look at the value of the 0, add 1 to it. So that's 1, 2, 4, 8 plus 1, 9. So this is minus 9. So 1 plus 1, 2. That's 0 with 1 carry. 1 plus 1 plus 0, 2, 0, 1 carry. 1 plus 1, 0 with 1 carry. 1 plus 1, 0 with 1 carry. 1 plus 1, 0 with 1 carry. The carry goes out. We discard it. So this is the result, 0. So minus 9 plus 9 is 0. So this is the two's complement addition. All right. Now again, this you need to do. All right. Now subtracting, skip, make your life easier. See, I used to cover before. Now this thing is very nice. This is very nice. Please look through this. Look through this and inspect. And how do you call it? Think about it. See what is happening. Look at the numbers in different circle, what is happening and how they are increasing. All right. We don't need to cover this. We used to cover it for the engineering. Okay. Multiplication of binary numbers, I will skip, even though people still cover it. I don't know why, because they probably have done it before. Okay, BCD addition. Back to the BCD. What is BCD? Binary coded decimal. Binary coded decimal. Remember, every digit is 4 bits only. While the hexadecimal, converting to binary, every bit, every digit is 4 bits, but it can go beyond 9. BCD, because it's binary coded decimal. Decimal is 0 to 9. So we're only allowed to use 0 to 9 only, no more than that. So the sum equals 9 or less if we add BCD. So let's say 5 plus 4 is 9. This is 5. This is 4. We add them. 9 is still 9 or less. Okay, if more than 9, then there is a problem. 1 plus 0, 1. 0 plus 0, 0. 1 plus 1, 0. 1 carry. 1 plus 0 plus 0, 1. So this is still 9. So we're still okay. The thing that you have to watch for is each 4 bits must be 9 or less for the BCD. If it is more, then we have to correct it. All right. So this is done. If we have 2 digits plus 2 digits, and there is no carry in between. Okay, let's see. So this 5 plus 3, 8, 4 plus 3, 7. No carry in between. This is not more than 9, so that we can need to carry to the next one. Okay, so that's this addition. You do it, it's straightforward. Okay, now no decimal carries were produced with no cross. Okay, BCD addition process is straightforward. If there's no decimal carries, okay, we'll see some examples. Okay, now sum greater than 9. When the sum is greater than, for instance, we add 6 plus 7 decimal, we get 13. But in BCD, see, this is BCD, even though it looks binary, but it is BCD, binary representation of the decimal. So 0 plus 1, 1, 1 plus 1, 0 with 1 carry, 1 plus 1 plus 1, 1 with 1 carry, 1 plus 0 plus 0, 1. So this is the result. Now this result, is it BCD? So BCD plus BCD is it BCD? BCD has to be 0 to 9. This is 1, 2, 4, 8. 4 plus 8 plus 1, 13. This is 13. It is not BCD. We need to correct it. Okay? Because more than 9 is not allowed. What do? We have got 1101. We add 6 to it. We have to add 6 to correct the result. Okay, so we add 60110. So 1 plus 0, 1. 0 plus 1, 1. 1 plus 1, 0 with 1 carry. 1 plus 1, 0 with 1 carry. 1 carry goes to the next position. Difficult to draw here. So this becomes now 2 digits. This is 1, this is 3, which is correct. But 1 digit, 13, is not allowed. Cannot be more than 9. But for hexadecimal, that's a different story. So BCD for 13, the 3 is alone, the 1 is alone. Okay. So if the result of the BCD addition is more than 9, we must add 6 to correct the result. All right. Again, if we have 2 bit digits plus 2 digits, 7 plus 5, 12. 2 plus 1, 7 plus 5, 12. More than 9, we have to add 6. Then 1 plus 4, 5 plus 3, 8. So that's okay. If that's also more than 9, and would there be a carry, we still need to add another 6. Okay. So this 47, this is 47 plus 4, 3, 5, 3, 5. This is BCD. Now, BCD is same as the binary. It's binary representation of the decimal. BCD, binary coded decimal. All right. So we add this 1 plus 1, 0, 1 with 1 carry. That's 2, 0, 1 carry. 1 plus 1, 0 with 1 carry. 1 plus 1 plus 1, 1 with 1 carry. 1 plus 0 plus 0, 1. Now this we add also 0 plus 1, 1. 0 plus 1, 1, 1 plus 0, 1, 0 plus 0, 0. So this is the result. Now this result, let's see. This is 7, okay. This one is 1, 1, 0, 0, more than 9, which is C. This is not allowed for BCD. How do you correct it? We add 6 to it. If there's any carry, we add it to the next. All right? So we add 6 to it, 0, 0, 0, 1, 1, 0. 0 plus 0, 0. 0 plus 1, 1. 1 plus 1, 2, that is 0 with 1 carry. 1 plus 1, 2, that is 0 with 1 carry. The carry goes to the next position. This one is added to that one. 1 plus 1, 0 with 1 carry. 1 plus 1, 0 with 1 carry. 1 plus 1, 0 with 1 carry. 1 plus 0, 0, 1. So this is the result. This is 8, 2. Now this is correct. All right, so for BCD addition, if the result of any digits addition is more than 9, we have to add 6 to it. If there is a carry, we have to move it to the next. All right, so this is BCD addition. Okay, this is also another example, same as that. Okay, summarize. Okay, you read that. Okay, now let's look at this one. 3-digit BCD addition. How do you add in BCD? Adding BCD, everyone will be alone. So 5 and 7 and 2, 1 and 4 and 6. Then you add digit to digit. If there's a carry, add it there and so forth. So this plus this, that, less than 9, okay, or more, no more than 9. Now this plus this, that, it's more than, say 1, 2, 4, 8. 8 plus 2 plus 1, 11. More than 9, so we have to add 6 to it. Okay? Then there is no carry out of that. Then this just goes with that straight away. Normally, okay, you look, if this number is more than 9, you have to add 6 to it. If there is a carry, you have to add to the next one as well. So go through this also. BCD subtraction, it's a bit awkward. Even they don't cover it here. So I don't remember covering it before because they don't cover it here. I used to follow this book. Okay. Hexadecimal arithmetic is the last thing. Hex addition and subtraction. Hex addition is very nice. Hex addition is very nice. Inshallah, this should take a few minutes. Now, hex addition, we need to use our hands. Okay, to add like we used to do when we were in the primary school. You have, 1, 1, 2, 3, 4, 5, 6, 7, 8. You still can do it, but with after 9 you say A, B, C, D, E, F. Okay, so A is 10. So that is B 11, C, D, E, F 15. Okay, hex addition, the largest hex digit is F, right? Because we go from 0 to 9, then A, B, C, D, E, F. For procedure is suggested, add 2 hex digits in decimal mentally. If the sum is 15 or less, can directly be expressed in hex digit. If sum is greater than or equal to 16, subtract 16, carry 1. Okay, it's the same thing. See, for the decimal, if more than 10, we carry 10. More than 20, sorry, carry 1. More than 20, we carry 2. More than 30, we carry 3. Likewise here, for hex numbers, 58, 5, 8 plus 2, 4. We cannot say 24 hexadecimal. 24 is decimal. 2, 4 hex. Okay, so say 5, 8 plus 2, 4. Now 4 plus 8, 12. That is C. Okay. 5 plus 2, 7. Okay, this is straightforward. Simple. Very nice. Okay. Now let's see with larger numbers. Now 4 plus B. Sorry, 8. Oh, I'm starting to get tired. I'm already okay. So now without looking at that. So 5, 8 plus 4B. You'll be given questions like this. So 8 plus B. B is 11. 8 plus 11, 17. Sorry, 19. More than 16 by 3. 16 will be carried. That is 1. What remains is 3. So 3 is there. Then 1 carry, which is that 16. 1 plus 5. 6 plus 4, 10. That is A. So A3 is the result. So in the decimal, we carry the 10 by 1. For the hexadecimal, we carry the 16. More than 16, put the difference, and then that 16 will be carried to the next one. Let's say, look at this one. Okay, example. D7D plus FA. What is the answer? D is 13 plus A is 10. That is 23, right? 23. How many more? We have more than 16. Only 116 there. So that 16 will be carried. 23 minus 16, 7. 23 minus 16, 7. So this is 7. And then 1 plus 7, 8. Plus F. F is how much? 15. 15 plus 8. 15 plus 8. Again 23. Sorry. 15 plus 8. 23. So we have 1 carry, that is 16. 23 minus 16, that is 7. And then we have 1 coming down. Is this correct? Is this correct? Okay. I didn't actually I didn't reach here. I thought this will be for next time, but I said no, let's finish it today. So FD 7D plus FA. Okay, let me quickly, where's my calculator? I thought it was here last time. Okay, you can always verify with the calculator, all right? Did anybody verify? Guys? So 7D plus FA. Okay, let's go to scientific. It's programming, is it? Scientific programmer. Then hex 7D plus FA. F, where is the E? A. Okay, equals 177. Yes. Did anyone check it? Guys, did you check this addition? Anybody? MashaAllah, we have so many guys there. We have 1, 2, 3, 4, 5, 6. Anybody? Guys, this will be in the exam. This is coming in the exam. And you need to show something like this. All right? Give me ChatGPT's answer and you get automatic 0. All right? So this is 3-digit addition. Okay? 3-digit addition. Again, F plus C, that's 15 plus 12. 27, we have one carry of the 16, 27 minus 16, 11 remains, that's B. Then 1 plus A, that's 10, plus 1, 11, plus 3, 14, that's E. Then 2, 3 plus 2, 5, so 5 EB. This is straightforward. You need to show this is 15, that is 12 when you do the addition. Subtraction, you need to borrow, subtraction. We didn't do binary subtraction. When we do binary subtraction, we always borrow 2. Just like for the decimal, we borrow 10, right? For the binary, we borrow 2. For the hexadecimal, we borrow 16. All right? Okay, I think this is the very last thing I want to cover here. Subtract that from this. Okay, this is, of course, you can do the negation and then, this is some more stuff here. Negation, that is 0 minus the value to find the negation, which is another way, of course. Okay, hex subtraction. Hex subtraction, okay. We need to borrow, or x minus y is x plus minus y. So you complement, you negate the subtracted number or subtrahend from the number that is minute, and you add to it. Okay, so we say x minus y is equal to x plus negative y. To find the negative y, add it to the x. All right, how to find the negative y? That is 0 or 0 minus the number. 0 minus the number. Okay, here they do the 2's complement, 1's complement plus 1. They get the result and then they add it. All right, please go through that. I'll leave this for you. Okay, let me see. 0 negation 0 minus the hex number. So if we have this 3A5, is it there? 3A5, was it that number there? No. Okay, that's my number. Okay, let's see this one here. Convert the subtrahend 3A5. Oh, that's the 3A5. Then 592. Okay, 592. Where is it? 592 minus 3A5. This is what needs to be done. Can we do it straight away? Can we do it straight away? Okay, let's see. 2 minus 5 cannot, have to borrow. 9 minus A cannot, have to borrow. 5 have to borrow from 5. Okay, so borrow from the 5. Okay, let's make this bigger. Borrow from the 5. We borrow 16. Okay, you need to write this down. Now, then, okay, the way we do this, you need to go back to the decimal subtraction to get this right. Okay, this is the way I like to do. I used to do. So this minus that cannot, we have to borrow. Before we borrow from this, of course we can borrow, but with this minus that we cannot, we have to borrow. So then we borrow from the 5. So borrow 1 from the 5. The 5 becomes 4. So 4 minus 3 will be 1. Okay, then now this 9, we borrowed 1 from the 5. Just a minute. I need to review this because I haven't prepared it at this stage. Okay, let's see how it goes. So 5 minus that. Okay, we go from here. Then we borrow from outside if we have to. So 2 minus 5 cannot. We borrow from the 9. We get 9 becomes 8, and 16 plus 2, that's 18. 18 minus 5, 13, that is D. Now this 9 has become 8. 8 minus A cannot. We have to borrow 1 from the 5. The 8 plus 16 will be 24. 24 minus 10, we get 14. That is E. Then this 5 becomes 4 because we borrowed 1 from it. So that's 4 minus 3 is 1. So this is the way to do it. You don't have to go through the way what they are saying. Or you can go to do negation, taking this into binary and do the 1's complement and then find plus 1 to get the 2's complement, which is this one, then add it to that. Still a big process. But for an IT expert that's going to be you should be able to do this. All right? So if we find the negation of 3a5, 0 minus that, so this cannot, so we have to borrow from one from these. If we borrow, actually, how much do we borrow? 15. We borrow for the first one. 16. Oh my God, 16. Then this 16, this has to borrow from it also, becomes 15F. This becomes 16. Then this has to borrow from it, becomes 15F. This becomes 16. Now 16 minus 5, 9. 16 minus 5, 11, sorry. B. Okay. 15 minus 9, B. 16 minus 5, 11, B. Then 50 minus A, 5. And 50 minus 3, C. CB8. C5B, C5B, or C5B, there it is. Then you add to that. So instead of doing the 2's complement, you do negation, which is 0 minus the hex number, this way. All right? I'll be very pleased to see you doing this in the exam. In the exam, you need to write on paper and scan. The difficulty will be in the quiz. In the quiz, I cannot let you write on paper because there is no way to upload, as far as I know. So you have to do it something like this. All right? This is always difficult for mathematics, this kind of exam platform, the quiz. Okay, guys, I think this is subtraction of the hex. Some examples there also. Please read this stuff. I think we will stop here. Okay, arithmetic circuits, no need. So we stop at 6, 8. Okay, guys, thank you very much for staying with me. Lucky, alhamdulillah, we managed to finish chapter 6. Next time we'll go to chapter 3. Chapter 3, we need to go until, okay, let me see. Chapter 3, I think we need to go until the NOR gates. Chapter 3 will do the Boolean with truth table, or, and, not. Okay, describe algebraically also, evaluate outputs also, 3-point implement from Boolean expression. Think NOR. Okay, next time we will go until, I think, up to here. So please review this part. And next time we will use Logisim, inshallah. Okay, next time we will use the Logisim. Okay, I mentioned to you last time Logisim.exe. Okay, make sure you download that. Make sure you download it. You try it out. You look at the tutorial. I think I showed you part of the tutorial last time. I will show you again, inshallah, next time. So Logisim, this is about 7 megabyte file. This is for experimenting using digital logic circuits and or gates. It's very interesting and very nice. Okay, guys, so please download this. I will send it to you. or you can download from internet. You need to have the Java virtual machine installed on your system, which most computers have. It will tell you, then you can do that, inshallah, and look at the tutorial. All right, thank you very much. Wish you all the very best. Stay safe and healthy, inshallah. Until next time, wassalamu alaikum wa rahmatullahi wa barakatuh. Yeah, there was, I think, let me